So in today's quiz, you are asked to balance some chemical equations. These aren't randomly chosen. These are textbook super types of chemical equations. The first reaction is known as an acid-base reaction. Now, the real key for solving and balancing these kinds of acid-base reactions is to pay special attention to your salt here. So let's do an inventory of all of the atoms of each element, and let's see why this salt is critically important. So we have 1 sodium, 1 oxygen, and 1 hydrogen in sodium hydroxide. How many hydrogens do we have in sulfuric acid? 2. Okay, we have 2 hydrogens, 1 sulfur, and 4 oxygens. Okay, now let's take a look at sodium sulfate. How many sodiums do we see? 2. So we have 2 sodium atoms and 1 sulfur and 4 oxygen. Okay, and in water we have how many hydrogens? 2. We have 2 hydrogens and 1 oxygen. Okay, so now the reason why the salt is really critical is it provides us insight into the amount of cation and conjugate base anion that we need present on our left-hand side. So for example, if we had to pick an element to balance first, what element shows up in the least number of compounds? What element is unbalanced that shows up in the least number of compounds? What was that? Sodium. Yep. So let's start with sodium. Let's start with sodium and let's play a game. So we want 2 sodiums on the right and we want 2 sodiums on the left. Okay, so our goal is to have 2 sodiums. One moment. Sorry about that. There was a mild interruption in the internet connectivity. So we want 2 sodiums on the right-hand side. And so how many sodiums do we have on the left? 2. Okay, so let's play a game. What times 1 would give us 2 sodiums? What times 1 would give us 2 sodiums? 2. Now, does everyone notice how the subscript for sodium in sodium sulfate is a 2? So that in turn tells us we need how many molecules of sodium hydroxide? 2. Okay, perfect. So we're making progress. We're now going to update our count. So we now have 2 oxygens and 2 hydrogens because 1 times 2 is 2. Okay, so we've revised our count. Now, looking at all of our elements once again, are there any elements where there's a different number of atoms of that element on both sides? So let's check. Sodium, is sodium balanced? Yes, so sodium, let's put a check mark. Okay, sulfur, do we have the same number of sulfur atoms on each side? Yep. Okay. What about oxygen? So we have a total of 2 plus 4, or 6 oxygens on the left, and we have 5 oxygens on the right. So is oxygen balanced? No. So then, my question to all of you, 4 plus 1 times what will give us our 6 oxygens total? 2. So we're going to fill in a coefficient for water of what? 2. Exactly. For those who are more math inclined, this sets things up algebraically, so all you are solving for x or guessing x. Okay, so now revising our count, now that we have a coefficient of 2, we end up with a total of 2 sodiums, 1 sulfur, 4 hydrogens, and 6 oxygens. So sodium and sulfur are still balanced. Is oxygen now balanced? Do we now have 6 oxygens on each side? Let's count. So we have 2 plus 4, which gives us 6 oxygens. Okay, and in terms of hydrogen, we have 2 plus 2, which gives us 4 hydrogens. So are hydrogen and oxygen balanced in this case? Yes, so we can put a check mark. So we've balanced every single atom of each element. And the way that we do that is we successively adjust our coefficients, we update our count, we look for elements that are unbalanced, and we balance them piece by piece. Now, Does everyone notice how the coefficient in front of sodium hydroxide is the same as the coefficient in front of water? Yeah. This is a critical aspect of acid-base reactions. The amount of hydroxides or the amount of hydrogens in your acid will directly match the amount of water molecules produced. So these are some tricks, because if you can identify reactions, you can balance them more efficiently. So let's put our 2, and now our equation is balanced. Does that make sense to everyone? Okay. So let's move on to the next class of reaction. This is one that you'll be dealing with today in lab a lot. This type of reaction is known as a displacement reaction, also known as a redox reaction. So let's do an atom count of each element. So in silver chloride, I have 1 silver and 1 chlorine. In aluminum, I have 1 aluminum. In aluminum chloride, how many aluminums do I have? 1. I have 1 aluminum, and how many chlorines? 3. Yeah. Okay, and in silver solid, I just have 1 silver atom. So, remembering our rule of thumb, what do we balance last? What do we want to save till the end? What was that? Yes, pure elements, exactly. So we'll leave aluminum and silver alone for now. Let's focus on balancing an element that pops up in the least number of compounds. So what element currently is unbalanced that shows up in the least number of compounds? Chlorine, exactly. So on the right, we have 3 chlorines. On the left, we have 1. So my question to all of you is, what times 1 would give us the magical number 3 chlorines? 3, exactly. So we plug in a coefficient of 3. Now, when you revise your coefficients, if you have 3 silver chlorides, will your amount of silver atoms change? Yes. How many silver atoms do we now have? 3. And this is really important. Don't forget to adjust your coefficients. Okay, perfect. So now chlorine is balanced. Chlorine is balanced. Aluminum is still balanced. What about silver? We now have 3 silvers on the left. So how many silvers do we need on the right? 3. And that we can just put the 3, since it's a pure element and it's an atomic element. So the amount of silver solid atoms is pretty easy to see why we need 3. Does that make sense? Okay. Now, in terms of the trick, so as someone who's balanced a lot of equations, looking at this 3. So if you take a look at the subscript for your anion in one of your compounds, be it reactants or products, you can cross it over into the coefficient of the reactant or product molecule that contains that ion. So for example, to have the same number of chloride ions as 1 molecule of silver chloride, I would need aluminum chloride, sorry, I would need 3 silver chloride molecules. And the reason why this works is this method is known as the least common multiple method, and essentially either your subscript or your coefficient, when multiplied together, will give you the total number of silver atoms. So if you want to, or chloride atoms in this case. So if you want to balance your anion, you just have to find the least common multiple between the coefficient and subscript on each side. We'll cover this more when we discuss redox reactions, and we'll discuss why this shortcut actually works. So it's always important just to pay attention to different types of reactions and how they can be quickly and efficiently balanced. Okay, this last reaction is another subclass of displacement, but this displacement functions slightly differently in terms of how you should balance it. So we have 1 calcium atom, we have 2 hydrogens and 1 oxygen in water. In calcium hydroxide, let's do a count. How many calciums do we have? 1. How many oxygens do we have? 2. Okay, and how many hydrogens do we have? 2. Okay, and in hydrogen gas, we have 2 hydrogens. equations. Okay, so following our rules, what should we balance last? What do we balance last? Yep, we're going to balance hydrogen and other pure elements such as calcium last. So then, what element should we start with? What element is unbalanced that we should start with? Oxygen. Okay, so now let's take a look. Let's take a look. So on the right-hand side, we have 2 oxygens, right? And on the left-hand side, we want 2 oxygens. So what times 1 would give us the magical number of 2 oxygens? 2, exactly. Now, do we need to revise our hydrogen count now? Yes. So then, 2 times 2 gives us 4 hydrogens. So now, oxygen's balanced, hydrogen's balanced, and calcium's balanced. So all we need to do is put a 2 in front of water and call it a day. Now, this one, it's a little bit harder to see if you're balancing via the anion method. But as this is a displacement reaction, does everyone notice how the subscript for hydroxide ended up as the coefficient for water? Again, all displacement reactions can be balanced using the least common multiple method, because what we're fundamentally doing is counting anions in our reactant and product side, and since atoms are conserved, the number of anions in ionic reactions are also conserved. Just a shortcut, a trick that I like to use. Any questions on balancing these equations? So, as you've noticed, classifying reactions gives us tools to quickly balance reactions. This will be the major theme of the next few chapters. So if we don't have any other questions, what we're now going to do is we're going to start to move towards a section where we're really going to need to have our nomenclature in place. So has everyone been practicing their nomenclature? I saw you were doing substantially better on nomenclature questions when I asked them on the pre-lecture quizzes. Don't let that skill degrade. Keep practicing it because you'll be using it a lot. So we're going to talk about today writing chemical reactions from text. Okay, we don't typically communicate in chemical formulas. We communicate using words to convey chemical formulas. So the word react, to give, to yield, those are signposts that you're going to draw a reaction arrow or write a reaction arrow. The phrase and signifies a plus sign, just like reacts with will signify a plus sign. Heat. What is the symbol for heat? Yep, the delta symbol. And then if you see the word catalyzed by or using a blank catalyst, you'll see your reaction arrow and you'd write the catalyst above the reaction arrow. So common catalysts are like iodide, anion. Okay. Not as important for this class, but it will be critically important in 102 when you deal with catalysis in detail. Okay, so this is all fine and good, but let's talk a little bit about the process. So let's suppose you are given a word problem or a chemical equation in word form. You're going to need to be able to read each of the chemical names and convert them into formulas with the correct states. So for example, we're given that carbon monoxide and hydrogen gas will react to give a liquid with the formula CH3OH. Okay, so let's take this apart, and first things first, we need an unbalanced chemical equation with the correct formulas and physical states. Once we have this unbalanced equation in place, we can begin our count. So carbon monoxide, what's the formula of carbon monoxide? CO. This is organic nomenclature. Mono means one. So CO gas. What is the formula of hydrogen gas? What is the formula of hydrogen gas? H2. It's a diatomic gas. This is why I have you memorize the common formulas of elements, because you need to be familiar when someone says hydrogen. If you wrote H, you will not be able to balance this equation. So if you ever run into an equation that you feel is impossible to balance, likely something went wrong in the name. Okay, CH3OH, we do technically, we did talk about organic nomenclature just a little bit. This is known as methanol, so we'll just write the formula of methanol. And what is the physical state of this compound? Liquid. We're given that in the problem. Okay, perfect. So this is our skeletal chemical equation. So as you see, without nomenclature, you wouldn't be able to even start this problem. This is why I emphasize nomenclature as a critical skill. Now what we're going to do is we're going to begin to count the atoms of each element in the reactants and products. So in carbon monoxide, I have 1 carbon and 1 oxygen. In hydrogen, I have how many hydrogen atoms? 2. Okay, in methanol, how many carbons do we have? 1. 1 carbon. How many hydrogens do we have? 4. And how many oxygens do we have? 1. Okay, so now let's take a look. Would someone like to volunteer and tell me which of these elements is unbalanced? Which of these elements do we have different numbers of atoms on each side of our chemical equation? Hydrogen. Yep, so let's circle hydrogen. Let's circle hydrogen. Are there any other elements that are unbalanced in this equation? No. Okay, so we've done our count. Now, as I've showed you this shortcut last class session, we're going to play a guessing game. We're going to guess a coefficient that would give us 4 hydrogens. So what times 2 gives us 4? 2. Yep, so we put a coefficient of 2, we multiply our atoms by our new coefficient, and that gives us 4 hydrogens. Now, carbon's balanced, oxygen's balanced, and hydrogen's balanced. So is this equation completely balanced? Yes. Okay, perfect. So we're following the same procedure as in previous sessions. This equation is relatively simple, so we didn't have to go through and recount multiple times, but we're going to start to approach equations that are a little more complicated. So let's try to delve into some more complicated examples. So we followed each of these steps. We just happened to get through these steps really quickly. What I want us now to do is to break into groups, and let's try to tackle a more meaty example. And in this first 2-minute block that I'm going to allocate to you, I want to make sure that you are able to write the formulas from the name for this statement. So I want you to focus right now on writing the formulas from the name. That's the first step, and then we'll come together to discuss. And if you have the formulas already, try to balance the equation. Yes. Yes. I made one change where I added things. So I have most of the examples are there. I just added a few additional. So that would be right after, or right after the hydrogen. This is what I don't know. I'm ready to learn. I'm ready to learn. Yes. Let's see. Copper 2 chloride, CuC. Well, chloride is Cl minus, and you get the number of chlorides by cross. Not a diatomic. Chlorine is diatomic. Yeah. Yes, exactly. Because the copper and 2 plus chloride is 1. Any questions? I don't have extra copies. I can have one to pass out towards the end of the lab period. Yeah. Everything going okay? So for copper 2 sulfide, then you cross the charges. Yep. So you can actually write a smaller ratio and just see. Okay, that's what. Everything going okay? Yep, exactly right. Now write the formulas for the product.
If it's a solution, that's the key rate or dissolving rate.
Yes, yeah, exactly right. Everything going okay? Yep, the only thing is when you're simplifying your ratio of charges, you want the smallest ratio of ions. So instead of 2 to 2, you simplify it to 1 to 1. Mm-hmm. How's it going? Oh, perfect. You have it all balanced and everything. Yep, exactly right. Yep, your formulas look good. Just remember the copper to sulfide when you cross the charges, you want the simplest ratio. Everything going okay? Yep, looks good. Yep, looks good. Your formulas look good. Wow, I'm really impressed. Everyone's been speeding through this example. They even already balanced it, but we're going to start from scratch, and I'd just like some volunteers. Copper 2 chloride. What's the formula of copper 2 chloride? CuCl2. Okay, this was obtained by taking copper 2 plus, chloride minus, and crossing the charges. So the key word for a solution, since it's a solution of copper chloride, what state symbol do we put? Aqueous. Okay. And now we're mixing with, combined with, so what symbol do we put? Plus. Okay. Sodium sulfide. Would someone like to volunteer a formula for sodium sulfide? Na2S. Okay. So just as a refresher, sodium is Na plus. The IDE ending, IDE, does that signify a polyatomic or a monoatomic ion? Monoatomic. So we have Na plus and S2 minus. We cross our charges. That gives us Na2S, and it's a solution. So we put the aqueous symbol. Okay, let's keep going with this. In terms of our product, copper 2 sulfide. Would someone like to volunteer a formula for copper 2 sulfide? CuS. Now, when we have copper 2 plus, S2 minus, we cross our charges. Now, instead of Cu2S2, we want the simplest ratio. So instead of Cu2S2, we just simplify our ratio from 2 to 2 to 1 to 1. Remember that from our nomenclature chapter, writing formulas from the name? Just be careful for that. Otherwise, you'll end up with some really tricky equations. And it's a solid, and sodium chloride needs no introduction. It's just NaCl, just table salt. Okay, let's now focus on doing an atom count. Let's focus on now doing an atom count. So I have 1 copper, 2 chloride ions, 2 sodium ions, 1 sulfur ion, or sorry, sulfide ion. I have 1 copper, 1 sulfur. I have 1 sodium ion and 1 chloride ion. Okay, now my question to all of you is, what element is not balanced? Sodium. Okay, so we have 2 sodiums on the left. So how many sodiums do I need on the right? 2. So just to highlight the logic behind this, 1 times 2 would give us the 2 sodiums and 2 chlorides. So we put a 2 in front of sodium chloride. Are there any elements that are still unbalanced in this equation? Let's check. Let's check. Copper, we have 1 on each side. Chloride's balanced. Sodium's balanced. Sulfide is balanced. A completely balanced equation. Does that make sense? Okay. Always do that check. You don't want to make a mistake on the exam and then realize it when I hand you your paper back. You have the tools to check your work. Okay, so let's now try and tackle another example. Let's try and tackle another example. And this time I'm going to show you a method that may seem like a lot of work, but it's a very procedural method for balancing equations that'll help you develop tricks for quickly balancing equations. So the table method is a very foolproof way. It's quite slow, but it's a great way to learn how to balance more complicated equations. So first things first, we're going to need an unbalanced chemical equation with the correct formula. So we're given an unbalanced chemical equation in this manifold. We have that all set up and ready to go. So our goal for today is we're going to count the number of atoms of each element in the reactants and products, and then we're going to add up the total number of atoms of each element on each side of our reaction equation. So this is a more procedural method of performing the count that we've been doing throughout this semester. Okay, so let's do some counting. So let's write our reactant molecule. So what's our first reactant molecule? Yeah, or phosphoric acid, H3PO4. Okay, and our second reactant molecule is sodium sulfide. Now that we have our chemical formulas in place, let's also write our product molecules. So we have hydrogen sulfide as one of our products and sodium phosphate as our second product. Okay, so we put our reactants on the reactant side, our products on our product side. Now what we're going to do is we're going to fill in and we're going to count the number of atoms of each element. So how many hydrogens are in phosphoric acid? 3. So we have 3 hydrogens. How many phosphoruses do we have? 1. Yep. And how many oxygens do we have? 4. Yep. In sodium sulfide, how many sodiums do we have? 2. Okay, and how many sulfur atoms do we have? 1. Okay, now we're going to hold off on calculating our total just yet. Let's look at our products now. What atoms are present in hydrogen sulfide, H2S? Yep, 2 hydrogens. And how many sulfurs? 1. Okay, for sodium phosphate, we have 3 sodiums, 1 phosphorus, and 4 oxygens. Okay, now what we're going to do is we're going to change pen colors, and we're going to look and find an element that is unbalanced. So what element is unbalanced in this case? Hydrogen, yeah, that's a good one to start with. So let's put a circle around that. What other element is unbalanced? Sodium, yep, let's put a box around that. Every other element is balanced. We have the same number of atoms of those other elements on each side. So our goal is to focus on balancing sodium and hydrogen. Okay, now this is where the least common multiple method really shines through here. So we have 3 hydrogens on the left, right? And we have 2 hydrogens on the right. Is that correct? So then, what is the smallest common multiple? What's the common factor between 3 and 2? What's the least common multiple? 6. So as our goal, we're going to shoot for 6 hydrogen atoms on each side. Where did we get 6 from? 3 times 2 gives us 6. 3 comes from here, 2 comes from here. Okay. So then, now that we have this idea established, let's guess a coefficient. So what times 3 would give us 6? 2. So we're going to guess a coefficient of 2. That in turn means we have 2 phosphoruses and how many oxygens? What's 4 times 2? 8. I personally find when you put things into a table, it makes it easier to see how the coefficient affects the atoms of each element, since then you're just doing a one-line multiplication. If you don't like the table method, that's okay. I'm showing you this table method because it helps you see tricks that you can use to balance equations quickly. Okay, now in order to get 6 hydrogens out on the right, what coefficient do I need for hydrogen sulfide? What times 2 would give us 6? 3. Okay, so that gives us 6 hydrogens and 3 sulfurs. Okay, let's try the least common multiple method again. This is a typical ionic equation. So for sodium, what is the least common multiple between 2 and 3. Wow, it sounds like I'm repeating something. Did we already find this least common multiple? What's the least common multiple? 6, exactly. So we'd want 6 sodiums on each side. So then all we have to do now is find a coefficient. So for example, for sodium sulfide, what times 2 would give us 6? 3. And for sulfur, 1 times 3 gives us 3. Okay. Now, what times 3 would give us 6? What's our coefficient for sodium phosphate? 2. Exactly. So times 2, we get 6 sodiums out. How many phosphoruses do we get out? 2. And how many oxygens do we get out? 8. Okay. The reason why I like the table method is it allows you to notice patterns that may be lost if you were just staring at the number of atoms of each element without organizing it into reactants and products. It also is a method that makes it very easy to revise your atom counts when you change the coefficients. Now I admit the table method is relatively slow, but it allows you, when you practice with different types of reactions, to develop shortcuts. So instead of having to go through and individually balance every single element individually, we noticed that if we develop a least common multiple, we can balance hydrogen and balance sodium, and lo and behold, the rest of our elements are now balanced. That's the power of the least common multiple method when applied to ionic equations. So all we have to do is go to our chemical equation and plug in our coefficients. So what coefficient did we choose for phosphoric acid? 2. So let's just put a giant 2 in front of phosphoric acid. What did we choose for sodium sulfide? 3. Okay, what did we choose for hydrogen sulfide? 3. And what did we choose for sodium phosphate? 2. So all we did to complete the problem is read off our coefficients from the table. Does that make sense? Even if you don't want to draw this exact table, you can use this logical thought process when you're counting atoms to balance your own equation. Does that make sense? Okay. Whatever method you're comfortable with. So let's now take a look, and I'd ask you to try and balance the following equation. And I'm going to write this off in a little bit larger font, so that way people in the back are able to fully see it, and that way we're able to proceed. So this equation is a little bit more complicated, but you can balance it using similar principles to that which we've already covered. So let's take a moment. At the very least, I want you to have an atom count for each of your formulas. And if you don't want to use the table method, you can just cross out the table and do your atom count however you prefer. I just want to see that you're comfortable balancing a little bit more complicated equations. Yes. going okay?
Yeah, I'm just doing it.
Okay.
I get so excited
Going okay?
And then the goal would be to see whether different values side circle and balance that.
Vete a comprar el torcido su. Lo viste acabado. Ya sabes, ahora no voy a decir.
Yo, pues, so let's try to pick the one that shows the least number of compound and that shows up in the most complicated compounds.
So just as a hint to everyone, if you want to pick to balance an element, try to balance the elements found in the most complicated compounds first, if you have a blanket choice. Everything going okay? Yep, that's good. Let's see. Yep, exactly right. And you started with silicon because it's found in the most complicated elements.
Yep.
So you could even technically have started with oxygen, whatever you prefer.
And then we can simplify these, right? 4, 8.
No, because it's 4, 4, 4, 4, 1, 8.
Oh, okay.
Yep. Yep, looks good so far. Any questions? Oh, we'll do lab 9 and 10. Everything going okay? Everything going okay? I would take a look at your HCl coefficient and just check to see if it matches the chloride count on the left. So I see a lot of reasonable responses so far. Even I've seen some completely balanced equations. So let's now come together and let's discuss. So first things first, I'm going to write each of my reactants. I'm going to write each of my reactants in my reactant column. Okay? And I'm going to write each of my products in my product column. Okay, let me rewrite this so that. Okay, perfect. So we now have our reactants and products. We've abstracted that information from our chemical equation. Now let's do a count. So in H2SiCl2, my question to all, or dichlorosilane, how many hydrogens do we have? 2. Okay, we have 2 hydrogens. How many silicons? 1. 1 silicon, and how many chlorines? 2. In water, we have how many hydrogens? 2. And how many oxygens do we have? 1. Okay. In this formula that closely resembles silica gel, it's an absolute mess to handle. How many hydrogens do we have? 8. How many silicons do we have? 4. And how many oxygens do we have? 4. Okay, and in HCl, we have 1 hydrogen and 1 chlorine. Now, I would hold off on your total atom count, and let's try to focus on the elements that are found in the least number of compounds first. And that's part of why I want you to hold off on the total atom count, because you can identify your unbalanced elements that are found in the least number of compounds just by comparing your reactant and product column. Now, if we had to take a choice, if you look at all of these elements, are the majority of these elements unbalanced? Yes. So if we had to take a guess, if we had to pick which element should I start balancing first, you're going to want to pick the element that is found in the most complicated molecule. And if you want to understand the logic behind this, if you change the coefficient for this molecule, it has a bunch of different elements in it, it's going to cause us, and it's going to unbalance a bunch of our elements, right? So we want to start with our most complicated molecules first. Does that make sense? Okay. So then, let's play a guessing game. So let's start with silicon, since it's the element that's found in the least number of compounds and that's contained in the most complicated molecules. So then, we have 4 silicons on the right. So my question to all of you is, what times 1 would give us our 4 silicons? What 4? Exactly. Now, as a consequence of this, how many hydrogens do we end up with? What's 2 times 4? 8. And how many chlorines? What's 2 times 4? 8. Okay, perfect. So we have our next count. Now, again, hold off on calculating the total. Only resort to the total when you are dealing with elements found in multiple compounds. We still have work to do here. We have 8 chlorines on the left. How many chlorines do we need on the right? 8. So let's put our target. Let's put our goal. We want 8 chlorines. So what times 1 would give us 8? 8. So as a consequence of this, we now end up with 8 hydrogens. What can you do? This problem just gets more and more annoying. So we have 4 oxygens on the right. So how many oxygens do we need on the left? 4. Okay, so our goal is 4 oxygens. So my question is, what times 1 would give us 4? 4. Exactly. And as a consequence, we now have 8 hydrogens. Okay, now this is where we're going to need to check some things. So let's check to see what elements are balanced. So silicon is clearly balanced. We have 4 on each side. Chlorine is clearly balanced. We have 8 on each side. Oxygen is clearly balanced. We have 4 on each side. Now, for hydrogen, you're going to want to check by looking at your total. So in my total, I have 8 and 8. So how many total hydrogens do I have? 16. Okay. On the top, on our right-hand side, for our products, I have 8 and 8. So how many total hydrogens do I have? 16. So is hydrogen balanced? Yes. This is when you rely on the total column to check your work, when you have elements that appear in multiple compounds. Does that make sense? Okay. So let's do a few more examples. I left some additional space just in case you take a little bit longer to go through the table method, or if you want to rewrite your table. So that's why there's some extra spaces in the notes. So what I want us now to do is to deal with balancing the equation using the table method from words. So what I want you to start off with, and for our first 2-minute block, I want you to try to write out the chemical formulas of each of these compounds. And if you're feeling ambitious, you can then try to balance. So let's just zoom in so it's a little more visible. And your goal is to process this sentence into an equation. That's your goal for right now. Everything okay? Any questions? Okay. Just make sure to cross your charges. Yep, looks good. Any
Oh, it does. It has a term.
Any question? Okay. Any questions?
Now, I would try to focus on writing the name of your nomenclature at all. Because on the exam, you won't necessarily have that. So the more you practice, even just once you have the formula, just write the name next to it. Try to code the meaning of the formula. Right? So that way you have some knowledge that you can access on. Everything going okay? Yep, looks good. I would just do an account just to check your work. Everything going okay? Yep. Everything going okay?
Yeah.
And the 2 symbol indicates the charge. Yep, looks good. Everything going okay? The 2 tells us the charge order. So you're almost right. So when you take PB2 plus and CL minus and cross them, the 2 subscript ends up on the corner. So that's 4. Yes. Everything going okay? Oh, nitrate is NO3. So just to give everyone a little bit of guidance, we've been working through the formulas. So let's try to establish the formulas that we're dealing with. So that way we can balance the equation. So lead 2 nitrate. So lead is Pb, and what does the 2 signify? What does the 2? The charge, so that it's 2 plus. Nitrate is NO3 minus. This is a textbook polyatomic ion. Crossing our charges gives us PbNO3 2. Okay, sodium chloride, we know we have Na plus and Cl minus. We cross our charges and we get NaCl. Perfect. Sodium nitrate. So what 2 ions do we have in sodium nitrate? Yep, sodium plus and nitrate, which is NO3 minus. We cross our charges, and that gives us NaNO3. Okay, let's now continue on. Lead 2 chloride. So we have Pb2 plus and NO3 minus. We cross our charges, and that in turn gives us, chloride, sorry. So it should be Cl minus, and that gives us PbCl2. So we write the charges of each ion, we cross the charges, that gives us the formula. So let's now take this equation and plug it into a table. So we have PbNO3 plus NaCl leads to PbCl2 plus NaNO3. Okay, so let's now do a count. I want you to take about a minute to 2 minutes and try to balance this equation given the formula, or at the very least, count the atoms of each element in this formula. And I'll be walking around and checking to see how everyone's doing. It's okay. It's okay. No problem. I'm not pushing any particular method as long as we can go. Yep. Sort of done the chart. Yeah. Yep. Yep, yep, it's good. Everything wrong? No, it's the same thing. I just wrote out the formula from the list. Everything going okay? Yep, looks good. So let's now come together to discuss this problem. If you're really inclined, there's an immediate solution, an immediate shortcut if we recognize what type of problem this is. Is this an ionic reaction fundamentally? Yes. And what did I tell you about ionic reactions? Do we have to think about atoms as much, or should we focus on ions? Ions. So let's do our atom count, and we'll discover a trick for balancing these ionic reactions, also known as exchange reactions. So writing out lead nitrate, we have PbNO3 2. So let's do our count. So we have lead nitrate and sodium chloride on our reactant side, and we have lead chloride and sodium nitrate on our product side. Let's now do a count. Let's now count the atoms of each element in each of our reactants and products. So in lead nitrate, what do we have to work with? 1 lead, okay. Okay, and how many nitrogens? 2. Yep, we have 2 nitrogens and 6 oxygens. Sodium chloride, we can see, has 1 sodium atom and 1 chlorine atom. Lead 2 chloride has how many leads? 1. We have 1 lead atom, and how many chlorine atoms do we have? 2. Sodium nitrate, we have 1 sodium, 1 nitrogen, and 3 oxygens. Okay, now, if we're looking at which elements are unbalanced in this equation? Sodium, yep. So one of our ions is unbalanced. What else? Oxygen, yep. Nitrogen and oxygen. I'm putting a box around them and grouping them because those are found in nitrate. So when we balance nitrogen and oxygen in this ionic equation, we're most accurately just balancing the ion nitrate. Okay, and chloride is also unbalanced. So let's focus on balancing our ions. So if we have 2 chloride ions on the right-hand side, how many chloride ions do we want on the left? 2. So my question to all of you is, what times 1 would give us 2? 2. And when we adjust our coefficient to 2, we end up with 2 sodiums. So we've unfortunately made a mess, and now sodium is unbalanced. But don't worry. So which element do you want to balance next? Sodium, nitrogen, oxygen, take your pick. All of them are valid choices. Sodium, sure, let's balance sodium. We have 2 sodiums on the left, so how many sodiums do we want on the right? 2. So we want 2 sodiums. So my question is, what times 1 would give us 2? 2. So then, how many nitrogens do we end up with? 2. And how many oxygens do we end up with? 6. So let's now go through and do our check. Let's just put a check mark. Lead is balanced. We have 1 on each side. Nitrogen's balanced. We have 2 on each side. Oxygen's balanced. We have 6 on each side. Sodium's balanced because we have, whoa. We can't look at we have to look at our total. We have 2 sodiums on each side, so sodium is balanced. And chloride is balanced since we have 2 on each side. So all of our elements are balanced. Now, let's do some pattern recognition here. Fundamentally, when we look at this equation, the 2 in nitrate, we have 2 nitrates on our left, right? Does this 2 for nitrate end up in our coefficient for sodium nitrate? Yes. So are we figuring out the least common multiple for nitrate ions? Are we figuring out the smallest amount considering the coefficient and the subscripts? Yes. So then this 2 in lead nitrate ended up as our coefficient for sodium nitrate. Likewise, let's pay attention now. Does everyone see this subscript 2 for chloride? We have 2 chlorides in our product. Did that subscript for chloride end up in the coefficient for sodium chloride? Yes. So is this a very similar dynamic to the least common multiple method? Yes, it's exactly the same. So for ionic equations, the key takeaway for you is you're going to balance ions. Okay, so let's now just transplant our coefficients up from our table. We have 2 sodium chlorides and 2 sodium nitrates. So quite simply, the subscript for nitrate ends up in the coefficient, and the subscript for chloride ends up in the coefficient for the compound that contains chloride. This is your textbook exchange reaction balancing scheme, or ionic reaction balancing scheme. Okay, so we learned a lot of how to balance different types of equations. Let's now practice on a range of different equations, some of which aren't in any of these classes that we've seen before. But we know how to balance equations in general, so let's try to hone those skills. So let's tackle the following equation. I provided you a table for your reference, but if you don't want to use the table, that's perfectly fine. So again, it's a word equation. So let's focus on balancing this equation given the statement for this reaction. And I'll be walking around and checking to see how everyone's doing. Yes.
So that's only kind of a herb it's supposed to be, but I have to simplify this for the test.
Yes, you want the simplest ratio.
So I would just like
Divide all of them by 3.
Yeah.
Yep. Okay. But you're on the right track. The logic is good. You just want to make sure the ratio of coefficients is as small as possible.
Okay.
Everything going okay? It's just because those are extra pages. If you want to show additional work, or students write in pen and make a mistake, they can just move to the next page. Everything going okay? Everything going okay? How are the formulas? Are you doing? What I would do is I would try to write the formula, and then you can check it. That way, you get some reinforcement. Everything going okay? Perfect. Wait. Potassium sulfate. I would double check the formula for potassium sulfate and barium. So, yeah, sulfate's charge is 2 minus. Everything going okay? Everything going okay? Yep, your formulas are correct. Everything going okay? Yep. Barium is barium 2 plus. Sulfate is sulfate 2 plus. Cross should be 1. Barium is really. Okay. Everything going okay? So check your so check. Actually, so your coefficients are fine. They should be the smallest possible ratio. So all of them are divide by 2. Yes. Yep, perfect. So let's come together and discuss this equation. Let's discuss and let's have some input. I want everyone to provide me some formulas here. Barium hydroxide. Would someone like to volunteer the formula of barium hydroxide? BaOH2. Exactly right. So let's talk a little bit about this. Barium is barium 2 plus. Barium has a 2 plus charge. Hydroxide has a -1 charge. We cross our subscripts, and that gives us barium OH2. Does that make sense? Okay. Potassium sulfate. Would someone like to volunteer the formula for potassium sulfate? Yep, K2SO4, K2SO4. So we have potassium plus, sulfate is SO4 2 minus. We cross our charges and we get K2SO4. Yielding, so yielding, that tells us we need to draw an arrow. Potassium hydroxide, would someone like to volunteer a formula for potassium hydroxide? KOH, exactly right. So we have potassium plus, OH minus, cross our charges, looks fine. Barium sulfate, would someone like to volunteer a formula for barium sulfate? Yep, BaSO4. So we have barium 2 plus, SO4 2 minus. We cross our charges, and remember, the ratio of ions should be the simplest possible. So instead of 2 to 2, it should be 1 to 1. Does that make sense? Okay. So now we have our count. Would we want to use the table in this situation, or would everyone just want to balance it the fast way? Yeah, let's balance it using our ionic shortcut. So if we're dealing with our ionic shortcut, we look at our ions. So I see I have 2 hydroxide ions on the left, right? So then how many hydroxide ions do I need on the right? 2. So I cross my subscript up to my coefficient. There we go. You can also do the same thing for potassium as well. Are all of our other ions balanced? Yes. So this is a fast shortcut. See how by looking in detail at a different type of reaction, we're able to quickly balance equations. This is how you develop intuition to balance equations quickly. Does that make sense? Again, a powerful case for understanding different types of reactions. So, I'm going to now teach you a shortcut that is invaluable for balancing very tricky equations. You're going to need to know this method, especially for combustion reactions. So, half notation is most useful when your reactions have a pure element. Remember how I said, in terms of the page number in the notes, this is page 30 in the notes. So, remember how I said that we balance pure elements last? Well, pure elements aren't just useful in terms of when you balance them in your chemical equation. They're also incredibly useful because they allow you to use a shortcut known as half notation. So here are the rules for half notation. You're going to balance as many elements as possible by adjusting the whole number coefficients. So you're going to balance this equation just like any other chemical equation that you've seen before. Okay. The modification and the change comes about in that you can now use fractional reaction coefficients to balance the chemical equation. You can now employ fractional chemical equations. Are there any questions in the back? No? Okay. So this fractional reaction coefficient is going to be used to balance your pure element. Now, as we've discussed earlier, a fraction, half a molecule, doesn't have physical meaning. So you won't end up with a final balanced equation in perfect form using this method. So to generate your proper balanced equation, you're going to multiply all of your reaction coefficients by the least common denominator and then write your corrected coefficients. So why are we going through and why am I showing you this method? Why do I want you to potentially use this method? Well, let's take a look at a pretty tricky equation that would be hard to balance under normal circumstances. You'd spend 10 to 15 minutes just messing with coefficients. Okay, so let's look at the equation. N2H4 gas leads to NH3 gas plus N2 gas. So following our method, so the key signpost that we're going to use the half notation method is that we see a pure element, nitrogen. Does everyone notice the pure element in this equation?
The pure element will always be by itself.
Yes. Yes, it can be either monoatomic, diatomic, or polyatomic, as long as it's a pure element in the chemical formula on the reactant or product side. Now, let's do a count. Let's do a count. So on the left-hand side, we have 2 nitrogens and 4 hydrogens. On the right-hand side, we have 1 nitrogen and 3 hydrogens. And from nitrogen gas, we have 2 nitrogens. So in terms of our total, we're going to have to rely on our total here. We have 2 nitrogens and 4 hydrogens. And we have 1 plus 2, which gives us 3 nitrogens and 3 hydrogens. Now, what we're going to start off by doing, is we're going to balance what element first? Do we balance pure elements first or last? Pure elements? Last. So what element is not found alone? What element is not found as a pure element? Oh, well, nitrogen is all alone here, right? So what element are we going to start with? Hydrogen. Exactly. Okay, now, as we discussed previously, a fast way for balancing out elements. So we have 4 hydrogens on the left. We have 3 hydrogens on the right. Can we use the least common multiple method? Yes. So then, my question to all of you is, what is the least common multiple between 4 and 3? 12. Okay, so our goal is we want 12 hydrogens on each side. Our end goal is we want 12 hydrogens on each side. So my question to all of you is, for hydrazine, N2H4, what times 4 would give us 12? What coefficient do we want? 3. Okay, and we end up with 6 nitrogens as a result. Now, my question to all of you, for ammonia, what times 3 would give us 12? 4. So that in turn gives us 4 nitrogens. Okay, perfect. So let's now add up our total. We have 6 nitrogens and 12 hydrogens on the left. And we have 4 nitrogens plus 2 nitrogens, which gives us 6 nitrogens and 12 hydrogens on the right. So this is the textbook method. This is the method that we've used time and time again to balance these sorts of chemical equations. The least common multiple method is actually derived from half notation. So this is one approach you can take. What I want to show you now is how you balance this equation using the half notation, the half coefficient or fractional coefficient method. So this is one approach that would get us to the right answer. Let's now take a slightly different approach and let's demonstrate this slightly different approach instead of the least common multiple method on this example. So anytime you see a reaction involving oxygen, this is where half notation will save you. So let's write this out. So we have P4 plus O2 leads to PO3. Now, the trick in half notation is that you're going to play a guessing game where you balance everything except your pure element first. So in this case, we have how many phosphoruses on the left? 4. So how many phosphoruses do we need on the right? 4. So we can guess a 4 for phosphorus trioxide. And now if we have 12 oxygens on the right, how many would we need on the left? 6. Okay, this is a perfectly valid method of balancing this equation. Let's show now an alternative approach where we use fractions. So this is the fractional coefficient method. So P4 plus O2 leads to PO3. So instead of guessing whole numbers, instead of having to resort to whole numbers, I'm instead going to guess fractional coefficients. So looking at my total, I have 1 phosphorus and 3 oxygen on the right. So my goal in this next section is to figure out if I have 4 phosphoruses on the left, what fraction times 4 would give us 1? What fraction can I guess that would give me 1? What times 4 would give me 1? 1/4. So we're going to guess the fractional coefficient of 1/4. Okay. Is everyone following how we obtained our fraction? Okay. You only put your fractions in front of pure elements if you can help it. This is a method used to finish off and balance pure elements quickly. Okay. We're now going to take a look at oxygen. We have 2 oxygens on the left, but our end goal is 3 oxygens. So let's try to guess a fraction. What times 2 would give us 3? 3 halves. And as a shortcut for this, you put what you want on top, which is 3, and you put what you have on the bottom, which is 2. So we get a coefficient of 3 halves, 3/2. So is this equation technically balanced? Do we have the same number of atoms of each element on each side? Yes. But can you just write this as your final answer and call it a day? No. So as our last trick, as our last ending, we're going to need to take all of our coefficients and multiply by our common denominator. So what's the largest common denominator on the bottom of all of our fractions? 4. So we're going to multiply all of our coefficients by 4. So this gives us P4 plus 6O2 leads to 4PO3. So we've reached the exact same conclusion, but we're using a slightly different method. And for those who are wondering, why do I even care about this? What is the use behind this? Half notation will save you when you're dealing with complicated equations that involve oxygen, where the least common multiple method runs into problems. It's not that you can't use the least common multiple method, it's just for very complicated molecules where your hydrogen and oxygen are found in multiple different molecules. Being able to quickly write a half coefficient for oxygen instead of figuring out the least common multiple will save you time on the exam. So this primarily comes up when you see oxygen. If you have to remember anything from this section, it's half notation. You should think half notation when you see oxygen. So it appears that we're out of time for today. I have some additional examples that I would recommend looking over. Your exam will cover all the way up to balancing equations, including very complicated equations. We'll save the bulk of stoichiometry for the next exam.